So we are going to be looking at McNema. The first one we're going to look at is chi-square for trend. As I said, we are looking at four things today. Chi-square for trend, chi-square for test of goodness of fit, McNema chi-square, and McPauka chi-square. There is somebody join us now. Okay, it's Isaac that is logging in and out. Yes. You know, I say so for this, when you want to assess whether a binary variable varies linearly through the levels of an ordinal variable, you use chi-square for trend. What do I mean by that? What this one means that you can just look at I prefer looking at a table that has example, not the one that just have some funny things. So when the outcome variable is dichotomous, there are two possible values, either yes or no, may or female, whatever. Is there good or poor? So when you have two categories of the outcome, then the exposure variable is ordinal. For it to be ordinal, that should have it has number one. It must have more than two categories. It must have at least two categories, and the category must be ranked. That's the meaning of ordinal. So if something is two categories, it cannot be ordinal. You cannot see a trend. Like when people measure blood sugar, you see blood sugar greater than this is diabetes, the other one not diabetes. It's not ordinal, just binomial, because though underlying variable is quantitative, but once you just put a cutoff, just 1 minute, just a minute. So we have outcome variable that is dichotomous, two categories. Exposure variable is ordinal. For it to be ordinal, of course, it has to be more than two categories and must be ranked. That's ordinal. So you want to know, for example, look at the example here now. Employment status is the outcome variable, whether somebody is employed or not. So it's binomial. It's two categories, yes or no, employed, not employed. Now, the level of education we determine employment. And the level of education, we have more than two levels. And these more than two levels are in hierarchy. You know that no formal, primary is higher than no formal education. Secondary is higher than primary. Tertiary is higher than secondary. So when you look at it from that perspective, you now know that the outcome variable is dichotomous, the exposure variable is ordinal. You want to look at the pattern now. You can see how many people have no formal education here is 15. How many have primary education is 85. How many have secondary education? 125. How many have 70? Tertiary education 75. But out of the 15 people that have no formal education, 5 were employed, which is like 3.3%. For primary school, education is 41.2% that are employed. For secondary, 64%. For tertiary is 86.7%. You will see that the percentage of employment increases as you are climbing the educational hierarchy. Sometimes you may see some break. Maybe at this one is 33, this one is 41, you may have 50 before you get to 80 something. Or you may even have maybe 30 or 39. Maybe that's just a small break. Or where we have that primary, the primary will be lower than no formal education, somehow. But the issue is that whether it is like that or it's like this, you need to put it to test to see if the trend, you can boldly say that as the level of education increases, employment status increases. Or at the level of education increases, the employment status decreases. It can be like that. You just want to see there is any trend. So when we talk about ordinary variable, it's not only education, even age group is ordinary, because you see something like less than 20, 10 to 29, 30 to 39, 40 to 39. You see that there is hierarchy. Whenever there is hierarchy in the exposure and the outcome is two categories, you can, if you do chi-square, piercing chi-square does not give much meaning. People do it too. You want no most of analysis. When we say good knowledge, good or poor knowledge, good knowledge, yes or no, or something happened, yes or no, infected, yes or no. We now put age group. Age group is ordinary. When you do the basic chi-square, you're supposed to even look for chi-square for trend to see, does it change? Education, profession, all those things that are ordinary, socioeconomic status, all those that are ordinary. You need, it's good to do chi-square for trend. We are not talking, there are some variables that are nominal. You cannot use it like marital status. There's no order there. There's nothing that says that marriage is superior to single, or the separated is superior to married, or widow is superior to whatever. So it's just any category. If you arrange them, you can just arrange them at your convenience. Maybe ethnicity, it's not ordinary variable, it's a nominal variable, in the sense that there's no one ethnic group that is superior to the other. Social, geopolitical zone is nominal, it's not ordinary. But when you are talking of education, level of education, social status, all those things, they are ordinary variable. Now, if you understand that, we move forward to see how it is done. So I would not even want you to bother yourself, because though I put the formula, the logic behind it, but what you just need to know there is that, look at the same table I put here now. All you need to do, is when you say something is ordinary, you have to put a score, arbitrary score, which is 1, 2, look like a Likert scale, 1, 2, 3, 4. For that, no formal primary, secondary. That is the extra column attached to the table now. Table I showed you before. There is the extra column. So is this, if you look at it, just one complex thing like this. Chi-square for trend is T1 minus CT2 over N bracket S square over V. What V is stated there also. So you just put in. So for me, I don't need to bother yourself. But if you actually want to see what you do here, how do you calculate the T1? T1 is calculated by multiplying the rank for each level with the category that are yes, the number that are yes, frequency that are yes. Look at it. 1 times 5, look at it. 1 times 5 plus 2, the rank for this 1 times 35 plus 3 times 80 plus 4 times 65. That's for T1. The T2, that one is looking at the total. Can you see? 1 times 15 plus 2 times 85 plus 3 times 125 plus 4 times 75. The other one is looking at the square of the rank, x squared, that is 1 square times 15, 2 square, which is 4 times 85, used to multiply the total also. Then the 3 square, which is 9 times 125, 4 square, which is 16 times 75. That's how you get the T3. So someone put it together, you get this answer. So don't bother yourself, but just for you to know the logic that you are trying to see how the thing vary along the time. So what I want you to do, you have the, let's just run it, you see it.
Hello, sir.
Yes.
Sir, please, I want to ask, this chi-square for trend is only for, you can only run it for ordinal variable and not nominal variables.
What do you mean by that? Yeah, because the what you are just saying is half truth, because you have to say that you are using it for binary outcome ordinary exposure. When you have two variables, one, the outcome is categories, is dichotomous, two possible outcomes. What do you value for the outcome? That is binary. Then the exposure variable must be ordinal. You cannot, if the exposure variable is nominal, you cannot use it.
Okay.
Of course, the outcome is nominal in the sense that nominal is special type that is only two categories. Dichotomous. Like if let's say diabetic, yes or no. Hypertensive, yes or no. All those things. Sick, yes or no.
Okay.
Yeah, the exposure must be ordinal. So I want somebody to, you see, the same socioeconomic file we used the other time on the day one. Read it now on your computer and share with us so that we can run it. Run this data. This data we just resetted on the table is there. You see the way it runs. It's actually the same way you just run ordinary chi-square. You go to crosstab, but you see that they don't write the trend. The expression does not write it as trend. We call it linear by linear.
Enable us, sir.
Okay, sorry. So you are enabled now. I share. Hey, you took us to Benin. It's okay. This is your wife, right?
Yes, sir.
That's great. So it's a princess.
Thank you, sir. Sir, thank you, sir.
Me, I think it's a princess. It's a thank you, sir.
Thank you, sir.
Okay, go on.
Okay. I'm trying to open this socioeconomic class.
Yes, socioeconomic class. And if you double click on it, it will.
Yes,
and it's coming. It will open now automatically. Okay. So you see social economy, you see employed and leisure of education there, employed and leisure. So go to normal chi-square, normal cross tabulation. Go to analyze. Descriptive cross tab. So the exposure is education, the role is education. The role is education. The column is employed. Go to statistics. Click on chi-square. Click OK. And continue rather. Okay. So enlarge the results, you can see. Yeah, scroll down, let's see it very well. Scroll the table down, the chi-square. You will see the same thing, it's okay. You see that the same table I show, that's what you have there. casino, formal, primary, second, tertiary, like that. And you will see Pearson chi-square he gave you with the degree of freedom 3. Because if you look at it, the number of rows is 4, the number of columns is 2. So 4 minus 1 times 2 minus 1, making 3. That's why the degree of freedom is 3 for normal chi-square. You see likelihood ratio chi-square also. It's a little bit bigger than the Pearson chi-square. You see linear by linear association, that is the chi-square for trend. If you look at the one with the, you see what we calculated is exactly what you have there. So, of course, when you run chi-square, it gives it to you. But whether you are dealing with ordinary variable, ordinary exposure or not, it will give it to you because it's already programmed. But you that know that it's not useful in that sense. So when you are dealing with ordinary exposure, like age group, like education, and the outcome is 2 categories like this, you can check. It makes sense to even use the linear by linear. And the degree of freedom is usually 1. Look at it. No matter the number of categories, doesn't matter. The degree of freedom is 1. So, do you get any question? So, linear by linear is the chi-square for trend. Any question?
Yes, sir. How did we get that 1?
Okay, where?
No, freedom. That is 1.
Yes, the degree of freedom is usually where? Is part of the calculation because the linear, if you look at, if I will go back and share my slide. So irrespective of this, is the degree of freedom is 1. And it's from the the calculation because simply because of the formula, because you have collapsed everything. You are not treating it as if it's a quantitative variable. Hey, you have to mute yourself. I don't know if you get what I'm saying. Let me share my this thing. Let me see if it's clear there. You have to mute yourself. Okay, maybe I should mute you. Your baby is disturbing you, right? You want to learn statistics.
Sorry, sir. I don't.
No, sorry. I'm just saying you want to learn statistics. It's just for you to mute yourself so that.
Yes, sir. So, sir, it's just a product of the calculation we're having that is 1 there. It's not that there was no special thing.
The issue here is that all chi-square for trend is irrespective of how many categories, the degree of freedom is 1.
It's 1, okay.
So the degree of freedom is 1. Forget whether the category, you can have 4 categories, 3 categories of exposure, or 5, even 10 categories, the degree of freedom is 1. Because it's treating it as a linear something, so it's not a matter of different categories. It's treating it as a linear. If you look at it, you just go and give score, arbitrary score 1, 2, 3, 4. No? So that's why the degree of freedom is usually 1. So any value,
sir,
yes?
Yes, sir. Then, how do we now interpret this result now? This
okay, thank you. Yes, the interpretation is okay. Let me share your screen again. Share that result. There's something I forgot for you to take. Go back and do this so that you put the percentage here. Go back to analyze, click on the analyze now. We didn't put, so that you go and put row percentage. Cross tab. Go to cells. Put row percentage. Click continue. So you see now, it does what put the percentage there, so that you can see that. You see how do you interpret it? You have already seen that the trend is significant. You see what is this trend? The observed trend is significant. What is the observed trend? You see that If you want to take, yes, employ for different categories of educational level. Look at the no formal education is 33.3% under yes that's employed. Primary education, 41.2%. Secondary education, 64%. Tertiary education, 86.7%. Can you see that the percentage, the proportion that is employed increases as the level of education increases? And if it is proportion of unemployed, you go to no, you see 66.7 for no formal, 58.8 for primary, 36 for secondary, 30.3 for tertiary. So whichever way you look at it, either you are looking at the proportion that are employed or the proportion that are not employed, the issue that it varies. So for the proportion that are employed, it increases with level of education. For the proportion that are not employed, it decreases with level of education. Whichever way, the trend, that trend you see is significant. Sometimes you may observe that it decreases or increases, but when you do the square for trend, it's not significant. It shows that that trend just by is due to chance. You cannot per se say that the level of the employment status varies with level of education. Do you understand now? Now I want you to go back. Sir. I want you to remove row percentage, go back and do the analyze again. So remove row percentage and put column percentage. You see something. We'll go to the cells and remove row percentage and put column percentage. You see, it doesn't change the chi-square for 10 or whatever. It doesn't change anything. What well, the change it, it may change your interpretation. What can you say about it now? Look at the percentages there. What will you say? Which group will you say within which group has the highest employment rate?
It's still the tertiary.
How do you know? How does it show here?
Okay, sorry, it is the secondary.
Okay.
The secondary has the highest number of employment rates.
Okay.
Because it has 43.2%, which is followed by the tertiary, which is 35.1%.
Okay, Dr. Ate, are you following? Dr. Ate. Is he there? Dr. Ate. Is there Dr. Ate is not with us. You unmute yourself.
I'm with, so it's just that where I am is not very good. So that's why I'm listening to everything.
Oh, you are still outside.
Yeah, I'm just parked by the road. A lot of noise.
Okay, you have not reached home.
That's why, but I'm following. I'm following.
So are you sure? Are you the one driving?
No, I'm parked. I'm not driving.
Okay, because you cannot drive and listen and be watching the same time.
Yes.
Okay, that's great. You see, Dr. Omorigwe, the reason that is that it doesn't actually show. It doesn't show that secondary is more employed. It's because if by the time I see this table, somebody do the table. Of course, really looking at him may do as if it's showing him. I will look at the direction of the percentage. I will say, how did they do the percentage? Is it row percentage or is the percentage along the exposure or is along the outcome? This one is along the outcome. It's supposed to be along the exposure. So if it's, what this one is saying that among all the 185 people that I employ you, 43.2 of them are secondary. 35% are tertiary. 80.9% were primary. 2% were no education. Though among those total that are employed, we have more of secondary education employed. It doesn't mean that employment status is higher with secondary education. Because that number 80 out of what? They are the majority. They are 125. So 80 being employed out of 125 is not up to 65 being employed out of 75 of tertiary people, graduate. Can you see that? So the number in that secondary category is much, is plenty. So even when you now put in the past, you look at the total number employed under them is much, is highest. But you have to compare it with how many of them, there are plenty. So the employment status is still highest in the tertiary. So that is why it's good to put the right percentage in your resource so that you don't misinterpret.
Okay, sir.
Yes.
How do we look at an analysis of a result? And we will just look at it and say this result, this analysis you have just made now is a column percentage you have used and not row. Because
thank you. I wanted to say before you ask it, that's a good question. If you want to know, if you had the percentage along the column, the one that add up to 100%, you know that it's along. But the one that does not add up to, whether it's more than it or it's less than it, that is not along. Like this one, if you add 2.7 to 18.9 to 43.2 plus 3, 35.1, it will give you 100%. But if you go and add 43.2, that for the secondary with 39.1, it doesn't add up to 100%. So if you do add them along the horizontal, they don't add up to 100%. It shows that it's not along the horizontal. You want to know is where it is along, you add it together in that direction. Like if you add it vertically now, it gives 100%. That shows that the percentage is along the vertical. It's along the employment, and employment is the outcome variable. It's wrong. You don't have the percentage along the employment, along the outcome. You add it along the exposure. So it's supposed to, so that is why row, if you have made the exposure your row, when you are entering those things, when we put education, row, employment, column. So when you get to your percentage, go and do row percentage. Unless if you put your exposure variable along the column, for you to get the right interpretation, you have to put your percentage along the column, because your percentage should be along your exposure variable. Is it clear?
Yes, sir. Yes, sir.
This is very, very crucial. You need to understand it, because there was a lady, but this is last year. So going for a O&G exam. So somebody has analyzed for her the result. Of course, somebody said, you should share the result with me, because he called me, share with me. We will look at it together soon. Or just go. I went through the result, and I said yes, because if you miss the percentage, it doesn't change the chi-square will be the same. It doesn't change. If it's going to be significant, it's significant. If it's not, it will not be. It doesn't change anything. Once you don't put the percentage right, your interpretation will be wrong. So they did it like this. They put it was having impression that something is higher than the other one. It's not true, because they put the percentage along the outcome. So I have to explain to her. She has to change it. And I think by that time she has already submitted the books. She has to change it and now have the final copy, the one is carrying, to take it to exam. So those are the issues. It's very, very crucial. It's very, very fundamental. And you see, yesterday we discussed it. And the day before yesterday, we discussed something about the percentage, the direction of the percentage. When we're looking at sex and employment also, I give impression that female are more employed. You put it along the outcome, which is employed. It gives the impression because we have more of the female, and among the people that were employed, males were more than female were more than male. But the issue is that in the total population of those people, female are more. So when you actually look at the employment status is higher among the male. So if you don't get the direction right, everything, your interpretation will be wrong.
Okay, I wanted to ask a question.
Okay, go on.
So basically, what we are saying is that for that particular table, so the question we are asking is, among those without formal education, how many are employed?
Yes.
Rather than saying, among those who are employed, how many have no formal education?
Thank you. Exactly. That's the way to interpret the sort. You interpret along the exposure. Don't go and you can just like if you contemplate male and female diabetes. How many have glycemic control? No, so glycemic control, no glycemic control. If you go and the total that have glycemic control, how many are male and female? You'll be wrong. But if you want to, because the outcome variable will be glycemic control, the exposure variable will be size. So you rather say among the female, how many have glycemic control? What proportion have glycemic control? Among the male, what proportion have glycemic control? You'll be able to know, is it higher among the male or female? Not that you go and say, among all the people that have glycemic control, how many are female or female are more? But who told you? You may have more female than male, far in that category. That number of female may not mean anything. Just a minute. So I think let's proceed. I think you have got it down right now.
Yes, sir.
Okay, let's proceed. You can stop sharing. Let me share my distance. Yeah. Okay. So let's go to the next one, which is chi-square. And these are just the step in run. You look at this, what you just run now. Instead of showing you, that's why you should run it yourself. Yeah. Let's look at chi-square for test. Chi-square test of goodness of fit. This type of chi-square is a single sample non-parametric test. One sample, yes, one group. Also referred to as one sample goodness of fit test. It is used to determine whether the distribution of a categorical variable follows a known hypothesized distribution, e.g. known pattern in the population. What do I mean by that? There are some things that are already known. Maybe the previous work that has been done, the pattern has been established. For example, now, in many literature, you see that this ABO blood group you see. In the population, we know that the blood group O is the commonest. It's commoner than all the other blood groups. It's around 40 to 50% of the total of the population, while the remaining one are shared by A, AB, A, B, and AB. So if it is established, maybe in your own environment, the blood group B in O is 45%, the other one 22, 20, 18, 15, everything add up to 100 like that. Now, in your own, it has been, when they say it's theoretical doesn't mean that in the initial time, it was practical. It was a study that was done, but it has been accepted as that is the normal. That's why they call it as theoretical. Even anything they say theory, there's a practical behind it. It's only after it has been believed that the notion has been held for long, they say it's theory. So the people that proposed, that brought the notion, it was based on practical experience. Now, in your own lab now, maybe you have the hospital, your lab in that same city. You now, people that come to the hospital, donate blood or whatever, you do their blood group, you are able to see that your own is like, it cannot be exactly the same. Your own, you may see that O is 39 or maybe 38, and this one, this one, this. Or your own maybe say O is 52%. It depends on what you get in your lab. You now want to compare, it's good, you want to compare, okay. This one I've got you, can we say the same thing as what is heard from the population? Can we say it's from that population? So you want to see, because the percentage of for your own and the theoretical one, for each category, the percentage will not be the same. But for the fact that they are not the same exactly doesn't mean that they are not the same. So until you put it to test that, okay, the test will show us that, okay, is it the same or not? So that type of test, where you are trying to test a distribution against a theoretical one or a already known one, it is called chi-square of goodness of fit, test of goodness of fit. And the example we have here is for the whole ABO block group also. The expected frequency of each group of the categorical variable can be equal or unequal. That is what we call the expected frequency now, is the theoretical one. For example, let me give an example. You may say maybe in our civil service in Nigeria, we may say that since we have 6 geopolitical zones, in our civil service, the federal character should reflect equally, that is, to be equal number of people from each geopolitical zone. If that's the case, you may want to test in a particular ministry now, let's see. But in your own, when you calculate the percentage from each geopolitical zone, you may not get the same equally as the other one. It may vary, but the fact that it's not exactly the same doesn't mean that it's not the same. So until you put it to test, you compare your own frequency with the one that they established in the law. If it is in the law that it should be equal, so that's so that the expected frequency should be the same, it should be equal. That is, if you divide, if there are 6 categories, you divide 100% by 6, it give you the percentage. Then maybe give you something like 16.something%, 60%, for all of them. Now, it may not be equal also. For example, this example of geopolitical zone, it may say that the federal capital will reflect the population. So the number you expect in the ministry will depend on, it will be proportionate to the population of that geopolitical zone. Since all the geopolitical zones don't have the same population. So in that situation, the expected frequency you are looking at is not the same. So if you want to compare yourself, you compare with the expected frequency. Now, let's look at the example. This example is the ABO block group. The table below shows the distribution of ABO block group in a tertiary hospital, laboratory, and the expected frequencies in the population. Can one infer that the distribution observed in the hospital significantly differ from that of the population? The population is the one they put in, I don't know, is it purple or orange or whatever, orange color. 21% for A, 21.1% for A, 80.9 for B, AB 50.4, O 44.6. That is what they gave in the population, in that population, the percentage from previous study that have been done. And you now do your own study now. You have your sample size 300. And when you do it, you calculate it to be A, 76 of them, which constitute your own 25.3%. B, 74 of them out of 300, which constitute 24.7%. AB is 31 of the 300, which constitute 10.3%. And O is 119, which constitute 39.7%. You will see your own percentage and their own and the theoretical one. It's not exactly the same. And that is what you want to test want to see this your percentage. Will you say it's the same as this theoretical one? That's test of goodness of faith. For you to do it, you need to calculate the expected frequency. Know that in your own, you have already gotten your own frequency, even though you also expect that percentage. You know, percentage is relative frequency, but the frequency itself is different. The observed frequency is the whole number, the count. Why? When you express it in percentage, that's relative frequency. But we are talking of the real frequency now. And what the theoretical one they gave you, they didn't give you the frequency. It's the relative frequency, the percentage they gave you. Can you see? Because they wouldn't have given you, because if they have to give you, it has to be, because their own sample size will be different from your own. It may be 3,000, maybe 200, maybe any figure. But they have already expressed it in percentage. But you have your own number. You have 300, and you can have the frequency and the percentage. So for you to calculate the expected frequency now, you already know your observed frequency. That's your own frequency. The expected frequency will be the frequency you generate from this percentage they have given you. So now, how do? You now apply that percentage to your own sample size. That is, if I'm to use my own sample, 300, what is the number that will constitute 21.1%, constitute 80.9%, constitute 50.4%, constitute 44.6%? And that is what we did in the second table here. Excuse me. Where you now put 21.1% over 100, that's the percent, times 300, because your sample size there, thank you, is 300. Let me spot it. Can you see? 21.1% over 100 times 300, it gives you 63.3. 180.9% for group B over 100 times 300, it gives you 56.7. 15.4% of 300 will give you 46.2, while 46.6% of 300 give you 133.8. These are the number they expected, even though, because you don't need to round it up, but it's just because you calculated, that's why it gives you decimal. It's a calculated thing. So it's not a real thing, it's a calculated thing. So you now, if you come here, the same formula, chi-square is observed minus expected square over observed. If you do it, 76 minus 60, 76, which is your observed, minus 63.3% for A over square over 63.3. It's not percent, 63.3. Then over A over 63.3. That's for group A. For block group B, 74 observed minus 56.7. When you square it over 56.7, for group AB, the 31 observed minus 46.2, you square it over 46.2. For group O, the 119 observed minus 133.8 expected, square over the expected. When you do it, you see something that when you, before you square it, when you minus it, half of it will give you negative value, because there are 4 categories. 2 categories give negative value, and the other category, 2 categories will give positive. If you add the positive and negative, it will be the same. That shows that it will give you 0. That is why they call it chi-square. They have to square it to remove the effect of the negative. So when you square it, so when you now add everything together, this is the chi-square. And the degree of freedom is the number of category minus 1. Number of categories of outcome is, that is, minus 1. The number of category of the block group we are dealing with here is 4. 4 minus 1 is equal to 3. The degree of freedom is 3. So the critical value of chi-square at degree of freedom 3 and at 0.05 level of significance is 9.488. So the calculated value is higher than that. That shows that it's significant. So you can say that your own block group distribution is significantly different from their own theoretical one. Any question before we run it? Any question?
So, sir, when we are going to chi-square for test of goodness of fit. We are just simply going to, I thought we are going to have the observe.
Sir, please, can you carry the critical value?
Yes. One person still ask a question. Let him ask his question first. I will answer you. Dr. Oborige, I don't know what are you saying. You said what?
So yes, sir. I thought that there will be an expected value, which is from the population, which we are going to compare the single, the observed value.
Yes, now that's it. When the expected value did not come as value, it come as percentage. You now convert it to value. That way, look at the purple. Look at the first table. That orange column. That is the expected percentage. Okay. So for you to convert it to value, you want to assume that if we apply, let's say 300 people, you apply it to, you now calculate what is 21.1% of 300, what is 80.89% of 300. You know, if you do all these percentages, we add up to 100. So what is 50.4% of 300? What is 44.6%? That's what we calculated here to get the expected frequency. So you have already got here in this column now. In the second table, we have calculated the expected frequency from the population. Whereas your own frequency is the one observed frequency. That's all.
Okay.
Is it clear now?
Okay, sir. Yes, sir. It's clear, sir.
Yes, Dr. Ati, your question.
So you said something about the critical value. So
yes,
at 3 degrees of freedom.
Well, this one is just for you to know, because if you run the computer, you don't even need it. It's just for you. By the time you run your computer now, you see the p value, if it's significant or not. But in those days, that's when we usually use this critical value. In those days, when there was no computer to generate p value for us.
Okay, with the table.
Yeah, we use it with the table. We're down. We're not using. You have to go and say, okay, what is the degree of freedom? 3. You have to go to the table of degree of freedom 3, and what is the critical value for chi-square degree of freedom 3 as level of your significance 0.05. You will see something like 9.488. You want to compare if your own is higher than that. Once your own is greater than that, that shows that it's significant. Because once your own calculated value is greater than that, that shows that the corresponding p-value will be less than 0.05. But now you don't need that. Let's go and run it. You see the result with your eyes. Kuro, kuro. Okay, who will run it with us? I think Dr. Ate, you can run it. Share. You will see ABO blog group. One of the SPSS file I sent to you. ABO blog group. Share it so that we run it. Okay, thank you. So, as you see, wait first. I want to explain something. Wait, remove that thing. Don't go to analyze, come out.
Okay.
You have to come here. So if you look at it, block group, you see 1, 2, 3. So if I coded A as 1, B as 2, A, B as 3, O as 4. You get it now? The sex, okay, we don't need the sex there. We don't even need all those. It's only that one you are dealing with. So go to, if you want to know if you go to variable view, you see where I label it. Or if you go to view here, you can label it for you. You can show the label for you. Can you see if you see how I label it? Click on it. Not sex. The blog group. It's not sex I'm talking of blog group. Can you see? 1 is A, 2 is B, A, B, 3, and 4. It's good to rank it. If you don't rank it, you won't be able to run into it. It will give you problem. Because it's good to code it. When you are doing the chi-square for goodness of, it's good to code that categorical. It doesn't really mean that it's hierarchical. It doesn't mean that it's ordinal. They just code you 1, 2, 3. Just because it will help you when you see where it will help you when we want to do analysis now. Now go back to that data view. Now go to view before data. Click on value label. Check that box, value label down. Yeah, check it. Check it now. Immediately, now it label for you that A, B, C. So it's those things you see there. So if you don't want it, you remove it. Just for you to know that. Now go to analyze. Go to analyze. Go to, it's not cross out this time, or go to non-parametric test. Legacy dialog. You see chi-square there. You know chi-square is a non-parametric test. So now you move the block group into that test variable list. You will see, if you come here, you see all category below here. You see here, yes, all category equal. If let's say the frequency is equal for all category now, you can just leave it like that, just run it. But the frequency is not equal for the expected. So you now put in the frequency. You remember, we say one is 63.3, the other one is, you have to remember, let me check. Because you need to use hand to put it. Let me share those values. So 63.3, 56.7, and 46.2. 63.3, 56.7, 46.2, 133.8. Yeah.
Last one, sir.
So what you do is 133.8. Add. Just say OK. Click OK. So start, okay. Start sharing and share the results. Yeah. Scroll down, let's see. It's okay. You will see that it gives you A, B, O. It gives you their own observed frequency. Can you see? Can you see? It gives you your own observed frequency here. Can you see? It gives you the expected frequency you just put in. It gives you the difference. If you remember when we are calculating the difference. So if you remove expected from the this, when the expected is smaller than the observed, it will be positive. When the expected is bigger, it will be negative. But if you add all the negative together and add all the positive together, it will give you the same value. Actually, if you are trying to add them together, it gives you 0. It just tells you the residual among them. And that's why the name chi-square, because you need to square it to move forward. So that's why just to give you that. But look at the chi-square, look at the degree of freedom 3, look at the value. It's the same thing as what we have calculated with R. So that's how to do chi-square of test of goodness of it. So you cannot see that R is significant. P-value is 0.02, 0.002. So that shows that the observed frequency is significantly different from the expected frequency, the theoretical one. Any question?
So the residual is different between observed and expected.
Of course, man. Yes. If you see, it's 0 observed minus expected. And that is the one you square and now divide by the expected in your calculation.
Okay.
So, any question on that? Any other question? Okay, if there's no question, let's move to the next one. Let me, you can stop sharing. Oh, I will override your share. So can you see my slide?
Yes, sir.
So you can see it's very straightforward. So look at the result just get now. Now let's look at McNema chi-square. The McNema chi-square, what it does, it compares proportion between two related groups. Two groups, and they are related. When they say two related groups, doesn't mean that maybe husband and wife. Now, I've already said many times that group in statistics does not mean individualized or group of subjects per se. It may be group of subjects, but not necessarily. It's actually group of data sets. After all, statistics is about data. Research is about data. So it's group of data set. If the group of data set is from different group of subjects, different subjects, we call it independent group. But if the group of data set is from the same group of subjects, which they took on two occasions. So you now have two groups of data. If let's say 300 people now, you do something to them, like for example, now you measure you classify them as hypertensive or not hypertensive for 300. Later, after some months, you come back to classify the same set of people. You have two sets of data now, but these data are paired. They are actually paired on the people. That is, it's one group, but it's two data sets taken on two occasions. That's why it's paired or dependent group or repeated measure or before and after. Those are the names they give to all those things. Paired, before and after, repeated, dependent. Whereas when there are two separate groups of subjects that the data is from, is independent. So McNema chi-square is all about in two related groups. They are paired groups, related, dependent group. And the outcome is categorical. And that outcome is categorical, is binomial. Somebody wanted to, Dr. Ati, you wanted to ask a question? So that outcome is binomial, is something like yes or no. So, but you are dealing with only one group of people, but you do the assessment two times. So it's rather, let's see an example, because me, I don't like talking theory. I want practical, so that from there you understand the theory. Look at this. Look at the second table. This second table, look at, it shows the hypertensive status of a group of adults before and after an intervention that involves lifestyle modifications. Did the intervention significantly influence the hypertensive status? You see, when you measure, there are 200 people. They measure their blood pressure and classify them as hypertensive or not hypertensive. That's the one we call before, hypertensive before. Yes or no? Can you see? It should be along the horizontal. No, we already said our exposure should be along the horizontal. So in a situation where you are having two occasions, you make the before to be something like the exposure, which is horizontal. You make the after to be vertical. Now, out of the 200 people, it's a workshop, so I want you to talk. So be telling me, how many were hypertensive before?
Out of
200
200.
total. Yeah, how many were hypertensive before?
The number that were hypertensive before, they were 60.
It's 60.
Yes. Yes. How many were not hypertensive before?
140.
Great.
140.
Okay. Yes. How many were hypertensive after?
40.
How many were not hypertensive after?
160.
You can see that before 60 were hypertensive, after 40 were hypertensive. So it shows that there is a reduction in hypertension. But that reduction, I want to say, is this significant? Is it just due to chance? Is it something significant? Now, if you look at when I was asking you a question, out of this, how many? All of them, they are along the periphery. Either the 60, 140, 40, 160, they are all total. But the green cells, these are the where the matter is. The green, the four cells. Inside the four cells, we have, just like the way Dr. Ati explained yesterday, we have two discordant and two concordant. Which one are the two concordants now?
The 8 and 108.
Yes, 8 and 108, because 8 people were hypertensive before, they were still hypertensive after. It is changed, the concordant. Then 108 were not hypertensive before, and they are not still hypertensive after. But we have these two other that are discordant, which is 32 and 52. 52 was hypertensive before, they were hypertensive before, they are not hypertensive after. 32 were not hypertensive before, they became hypertensive after. So if you look at it, those ones that are not changing, 8 and 108, nothing concerning them about this calculation. It's only these 32 and 52. The change, the movement from one to the other, or movement from the other to the one. Now, if no hypothesis was to be true, you expect the same number of movement from hypertensive to non-hypertensive should be the same as from non-hypertensive to hypertensive. So if both you have 32 and 52 that are discordant and that are changed, if no hypothesis has to be true, if that intervention did not do anything, the change is not significant, what do you expect to be in that cell where 32 is? What do you expect to be in the cell where 52 is? Can we answer this?
Can you come again?
You know, we have already said that nothing concerns you about 8 and 108, because those ones, they didn't change. What they're going to use to calculate is the 52 and 32. And the 52 and 32, 52 was hypertensive before, it became non-hypertensive. 32 was non-hypertensive before, it became hypertensive. Now, we want to see if non-hypothesis were to be true, if there's no change, we expect the same number that move from hypertensive to non-hypertensive to be the same number that will move from non-hypertensive to hypertensive. How do you get those numbers? Because they are more like the expected value there. How do you get it? Let's move further. So can you see how we get the number now? How do you get the number?
We just subtracted.
The 2 and dividing.
Yes, you add the 2 and divide by 2. Because the total change is 52 plus 32, making 84. If actually there's no difference, the change that moves from hypertensive to non-hypertensive is the same change that moves from non-hypertensive to hypertensive. That 84 should be equally shared among them. So if you divide the 84 into 2, it gives you 42, 42. That is the expected value in each of those two cells, the discordant cells. Does it make sense?
Sir, I didn't understand it, sir.
Dr. Ate, do you understand it?
Yes.
Okay, explain what you understand.
So the expected value is trying to look at the discordant for the discordant columns. So if there was actually no change, if the intervention did not work, we expect that the null hypothesis should be true, that there will be no change between this group that became the group of people before and after. So it means the column where they were hypertensive before and not hypertensive after, and then they were not hypertensive and became hypertensive after, should be exactly equal to each other. So to get that expected value there from this observed value that we have before, you have to add the observed value in the two discordant cells and divide them by 2 so that you have the exact same number in the discordant cell for the expected values.
Thank you. Dr. Warigo, do you get it now?
Yes, sir.
Okay, that's great. So,
Yes, sir.
since those are the only two you are using, so all you need to do is just to say, okay, observe, look at it, 52 minus 42 square over 42 plus 32 minus 42 square over 42. Of course, if you did square it, if you remove 52 minus 42, it will give you 10. If you remove 32 from 42, it give you minus 10. Both of them will cancel out. But because you square it, you remove that effect, whatever you get, that's your answer, 4.76. But the intelligent people came with an idea that there's a shortcut. Instead of you to even be calculating expected or unexpected, you can actually say the difference in the discorder squared over the addition of the discorder. If you minus the discorder, you square it, you now add the discorder to divide it. It will give you the same. Can you see how short it is? Very simple. The difference of the discordant square over the addition of the discord. It doesn't actually mean which one you remove from which. Because when you square it, if there's any negative, it will remove it. Does it make sense? If you look at that's what we are now DDNI, it's the same answer you get. The same answer you got with this one, it's the same answer exactly you get with this one. Does it make sense?
Yes, sir.
Now, the degree of freedom is 1. How do we get it as 1? The degree of freedom is number, K is the number of category, which is 2. Then times K minus 1, which is 2 minus 1, divided by 2. All those things will give you 1. But you understand the logic of that degree of freedom later when we do the Mark-Nemer-Bowker. So let somebody share so that you share, you see hypertension before and after, hypertension before and after. That's the name of the file. Let somebody share with us, hypertension before and after, so that we run this same data set you have here.
Hello, sir. Are we there?
Yes, yeah. So you see the hypertensive yes or no. If you go and all these 1 and 2, I see is yes or no. If you want to know, you can go to view. You go to view, you click, you go to see. Go to view and click value label. You go to see that is labeled yes or no. Yes is 1, no is 2. Click on it now. Click on the view. Then value label. Yeah, click on that. Can you see? You can see now. So it's labeled yes or no. So now, It is say you see before and after. Go to analyze. It's the same chi-square. Go to cross-tab. So the row, which one should be on the row? Which one should be on the column now? Eh?
The row will be hypertension after.
Roll it should be after hypertensive before now.
Okay, exposure.
The before should be the exposure now.
Okay, yes.
After should be column. So go to statistics. Click on statistics. Are you there? Click on statistics now.
I've clicked on it.
Okay.
I've clicked on it.
Okay. Click on McNema. You see McNema. Lower right corner. McNema. Yes. Click continue. So you don't just say okay. All those percentages, you don't need them. Yeah.
Can you see it?
Yes, enlarge the result now. So you will see, you know something? You will see one thing, you see that table is replicated here. One thing with McNema, can you see how simple you can calculate it? But there's no software that is able to calculate it. There's no program language that is able to calculate it. You see how human brain is powerful. But they can show you the p-value. So it's a joint project and you can use hand to calculate, and you cannot calculate the p-value. The computer will calculate the p-value for you. So that's the way to do it. You use your hand to calculate it, and the computer will give you the p-value. And it's very simple. The difference in the discordant square over addition of discordant. So you give you the value, but the p-value will be, if you run it with expressor, it gives you the p-value. Any question? So this one is showing that it's significant, 0.038 is significant. Is it clear?
It's clear. So sir, you mean there are different types of chi-square?
Yes, now.
So we will be using Pearson's chi-square all over, all this while.
But there are situations you cannot use Pearson chi-square. So, like this situation now.
Okay, thank you, sir.
Welcome. Now, subject, let me continue. So we go to the last one, which is McNema Bowker. So this is the result we just did now. McNema Bowker is an extension of McNema. So without wasting time, when the categories, there's some academic thing, when the category are dealing, it's the same thing with McNema Bowker. Something clear observation before and after on the same group of it. But what you are measuring now, instead of two categories, is more than two. Either 3 or 4 or anything. The category of the outcome is more than 2. So instead of yes or no, it may have 3. Like for this example we give now, is socioeconomic class before and after COVID. You know, some people, they become rich through this COVID. They were poor before. They became by the thank God for COVID. Some people, they are blaming, that COVID destroyed this last year, destroyed their business, everything. So some people became lower. Their level dropped after COVID. While some, they climb up. Like people that are selling food now, I think they climbed up during COVID and after COVID. The other people that are suffering. The effect of COVID now has caused inflation. But whenever there's inflation, people that do business, especially selling food, they are the one that make. Now, this category, you call it K, number of category K. So here, the internet just went out in a few minutes. Can you hear me?
Yes, I can hear you now, sir.
So what the hell, yeah. So let's just quickly finish it. So now, you have different categories. So if there are 3 categories, it will give you 3 by 3 table. If there are 4 categories, so 3 by 3 table, we're going to have 9 cells, like what you are seeing here now. If it is 4 categories, it will be 4 by 4 table, 16 cells. And that was what we were trying to explain here with this table. There is a little bit somehow. Now, number of categories, if the number of cells will be K. If category is K, if the number of categories is K, the number of cells will be K times K. So like when we have 2 categories now, number of cells is 4. When we have 3 category, number of cells is 9. When we have 4 category, number of cells is 16. 5 category, number of cells is 25. Like that. So now the number of concordant, so we talk about concordance and discordant cell. We say that we have 2 concordant and 2 discordant cell with McNema. So if you look at the first one now, is actually McNema category because there are 2 categories. So we have 4 cells, and the number of concordant cell is 2. Number of discordant cell is 2. Number of pair of discordant cell is 1 when you pair it. So the degree of freedom is equal to the number of pair of the discordant. Can you see? Now, the one we are having now, example we are having about COVID-19 socioeconomic class stuff, is 3 cells, 3 categories rather, and we have 9 cells, and we have number of concordant cells 3, number of discordant cells is 2, number of pair of discordant cells is 3. So don't let us talk much about theory. And the degree of freedom for it will be 3. Can you see? Now, let's move forward. Now, let's see. Let me now explain, because I'm sure this is where Madam Dr. Ati was having problem, because she watched the video. Now, if you look at it now, this is the example I've just given now. You will see that there are 3 concordant cells. Look at this. This one, 6 people were upper before, upper later, upper socioeconomic class. These 36 were middle before, middle later. These 93 were lower before, lower later. So the concordant cell, they are along the diagonal. And the concordant cell will be equal to the number of categories. Of course, makes sense. Because it's when it meets itself, upper, middle, lower. So if you have 3 categories, in the concordant cell and the diagonal will be around the diagonal where they meet. But the discordant cell, you can see here, for each concordant cell, you are going to have 2 discordant cells. Look at this one. Look at this discordant cell, they occur in pairs. And that's why I give them the same color. Look at this one that look like purple now. What this one is that this 14 was upper before, it become lower. It become middle rather. The opposite is that these 7 were middle before, it now became upper later. If you look at the green, they are the discordant pair. 15 was upper before it became lower after. 22 were lower before it became upper after. Now, if you now look at this blue pair, 57 were middle before it became lower after. 50 were lower before it became middle after. So you see that even though yes.
No, sir.
Yes.
The values they are not the same values. How are they the same before and now the same when they are two different values?
It's not the value that matters. It just will tell you that the opposite. The value you are seeing there is the number of people in that category. But the logic for preparing is the way they come. Look at this. These 14 and they were people that were in upper socioeconomic class before COVID-19. They dropped to lower, they dropped to middle after the COVID-19. Why the 7 were in middle class before, they dropped to upper. Is it not the opposite? Eh?
Yes, sir.
Some people were upper before they dropped to middle. Some people were middle before they came to upper. So that's for the green one. These 15 were upper before they dropped to lower. These 22 were lower before they climbed to upper. That's the opposite. For the blue, 57 were lower the middle before they dropped to lower. 50 were lower before they climbed to middle. You get the picture now, you see the pair now. So they have their own pair.
Okay.
Now, it's the same logic for the calculation of McNemer. It's the same logic. All you need to do you need to calculate the expected value. This second table, somebody is making noise. You have to mute yourself. This second table, try to calculate the expected value. Please off your this thing. Mute yourself. Now, this second table is to calculate the expected value now. You will see, you have to calculate it for each of the usage. The same way we did it for so it's like as if you are having 3 McNemer inside this McNemer Balkara, because there are 3 categories. There are 3 pairs of the discordant cells. I've already told you the concordant cell does not have any role in the calculation of anything McNemer or McNemer Balkara. Now, look at for the purple one now. You see the expected value here. What did we do before? Is to add the 2 together, 14 and 7 divided by 2 give you 10.5. 14 and 7 divided by 2 give you 10.5. That is when you add it to divide into 2, share equally among them. The same thing we did for the green one. You add the 50 to 22 divided by 2, it gives you 80.5, 80.5. The same thing with the blue one. 57 plus 50 divided by 2, it gives you 53.5, 53.5. Those are the expected values. When you now come and feed it in here, for each of the pairs of the discordant cell, it will be 2, 2, 2 now. This will be 6. You don't fit minus 4, 14 over minus 14 minus 10.5. That is the expected for this cell minus that is observed for this cell minus the expected. For this one, observe for this one minus you do it like that. You calculate the chi-square. It gives you 4.116. The degree of freedom I've already told you. Is the degree of freedom is k minus 1 over 2. So here now the degree of freedom is 3. The critical value for the chi-square at the degree of freedom of 3, for the degree of 3, and 0.05 level of significance is 9.45, 9.488. Just like the way we look at it, we assess it. That time. The 3 degree of freedom, the critical value is 9.47. And this one is 4. That should is not significant. So here now we can boldly say that COVID-19 does not influence the socioeconomic status. So if you look at the alternative way of calculating just like what I did, all you need to do, you can remove the difference between the discordant over addition, square over addition of the discorder. For each of them, you can do it. Look at it here. The difference between 7 and 14 is 7. 7 square over 14 over 14 now. Over 21, which is addition of 7 and 14. Can you see? This one, the difference between 22 and 15 is 7. 7 square over addition, give you the addition is 37. This other one also, look at it. The difference between 57 and 57, 7 square over addition of the two. If you do it, it gives you the same way, the same answer. Whichever way you use, it gives you. So any question before we run it? Any question? It's quite interesting.
I have a question, sir. So for this one, the degree of freedom is always equal to the number of categories.
Wait. Check this. Come and check. Come and check. You see that it's not like that. The degree of freedom, if you look at the last column, is the degree of freedom. It's not actually, it just happened for 3. You hear me now? For that 3, but if it is 4 categories, the degree of freedom will be 6. If it is 5, it will be 10. You get it now? So the logic behind it, how many times can you pair? You can say that it is equal to the number of the pair. The degree of freedom is number of the pair of the concordance, number of pair of concordance. Look at it here. So the degree of freedom is the same time number of pair of concordance. And number of pair of concordance is not always equal to the number of the category. Though the number of diagonal, the number of concordance will be equal to the number of category. But the number of pair of discordant is not equal to the number of categories. Not always. Do you get it now? And the number of pair of the discordant that will give you the number of the degree of freedom. So let somebody share. You will see the same socioeconomic that the one we shared before. That socioeconomy something. Questionnaire, the one we used before for chi-square for trade. Somebody to share. Have you reached home, Dr. Ati?
No, I'm on the road, sir.
Okay, you just stop for this lecture. Oh boy, you are safe.
I don't want. Yes, it's a safe area. It's safe, sir.
Okay.
It's safe, thank you.
Okay. So now you see socioeconomic class before COVID, socioeconomic class after COVID is there. Now go to analyze. If you go and look at it, we have already upper middle class, we have already coded all these 1, 2, 3, middle, upper. If you go to the view now, you see. Go to analyze, cross tab, just the same way. Move before as row, after as column, and go to statistics. Click on McNema. Click continue. Click OK. You don't need cell. Click OK. You don't need all this cell. Okay. So stop sharing and share the results. You can see, you contabulate and show you that table. Look at the chi-square 4.11 it's not significant because it's very small. Look at the degree. You will now see that this one, if you calculate chi-square for you, the computer is not unlike McNema. For McNema, it will calculate. That's that when the category is more than 2, so it will be able to calculate it for you. And that's McNema Bowker. Can you see? And it's not significant. Degree of freedom 3. So now if you are showing it in a table in your result, it's not like the way you showed the other type of chi-square. What you do is that if you want to show the table now, you do like you now put percentage this along the total, along the row, and along the column like this. For socioeconomic class before COVID-19, I will put 35 bracket. What 35 over 300? What is the percentage? 100 over 300, what is the percentage? 165 over 300, what is the percentage? The same thing also I will do for the horizontal value, which is the vertical rather. I will do it like that. It's the periphery that will have the percentage. Those middle, they don't have this percentage. Don't show them. It's just there to show how the changes occur. Does it make sense? Any question? So if you have questions,
sir, I didn't get where we add those percentages, sir.
If you want to do what I'm saying, okay, let me see. Go back to the analyze. Go to that place where you do. Why did you remove? You can access it from the result. You can see analyze there now.
Yeah.
You can access analyze there now. And you go to cross tab now. Let me put descriptive statistics cross tab. And go to sales. Go and click total. Total percentage. Total percentage. 100% total. Yeah. Click continue. Okay. He didn't give you the total percent. He didn't. Okay, don't worry. Click. That's that you have to click. Go back and click both row and column and click total. I thought it's supposed to percentage total is supposed to. Okay, click on row and column. Look at it now. You give the row and column for all of them. Let's see now. But you don't need the one in the middle. What I was saying is that look at that 35 vertical. If you look at the vertical percentage, this percentage you give. Anyway, okay, I don't know which one you did, whatever. You will see what I just want to establish that you don't need to put all those ones in the middle. Those you don't need to put that percentage. The total 35 over 100 and over 300. What is the percentage? 33 100 over 300, 165. That is what you are supposed to put in your table. Then the one that is for before now. No horizontal, middle, upper, and lower. Then after middle, upper, middle, and lower, you put their percentage also. So those the one in the middle, you just leave them as ordinary figure without putting percentage. That's what I said. Okay, any other question? No more question?
So the PDF of this.
The question I have is, okay, go ahead, sir.
Okay, the PDF we are using now, sir. Is it the one used for lectures, sir?
Which PDF?
The one you are into lectures now. Can we see it in the website?
This PDF, yes, the slide is there. It's on the website. If you register, this slide is there.
Okay.
Where you can download the slide.
Okay, sir. So, Madam Ati, please go ahead and ask your question.
Madam Ati.
To clarify, you
Okay.
said about the parametric and non-parametric chi-square.
Which one? There's nothing like parametric chi-square. Chi-square is non-parametric.
Oh, it's okay.
They just decided to put the other one, all those to come on because it's about cross tabulation. They now gather it to many other things which do cross tabulation, like you want to do kappa, you want to do some cost reliability, or you calculate odd ratio, confidence interval, you need to cross tabulate. That's why they put most of the chi-square under that cross tabulation. But the one they don't need to cross tabulate, that you don't need two variables, is the one for goodness of it. You don't need two variables, it's only one variable. That's why they now put under the non-parametric. Chi-square, all the chi-square is parametric. They are all parametric.
No, they are non-parametric.
They are non-parametric. Chi-square are non-parametric. Did you get me?
Yes,
oh, yes, sir.
So you can drive home now. Your husband is waiting for you.
Thank you, sir. Just one more question. It's not related to. It's related to the unending part of this lecture and yesterday's lecture.
Okay.
Interpretation of odds ratio and relative risk.
Okay.
So you said odds ratio is a proxy for the relative risk. When we are interpreting the relative risk, we say, let's say we got 10 as our risk ratio. So we say people that smoke are 10 times more likely to develop lung cancer than people who don't smoke.
Yes.
So for odds ratio also, we say the same thing, or is there ever a difference?
No, it's the same thing. Don't mind it. It's the same. It's the same. Don't mind it. You know, many people, they just say the odds of, you don't need to put the odds. You just use, if you remember, you just use odds to represent the risk because you cannot calculate the risk already. You now represent the risk, you now use odds to estimate the risk. So it's the same interpretation. So some people say the odds of this is not right. In fact, it's confusing. It is confusing. It's the same. When you get the odd ratio, these people are more likely to do simple. 10 times more likely. It's the same interpretation. Because odd ratio is a proxy to relative risk. It's a proxy. So please, let's show our face. So let me show on your camera because I have to be sure that I'm not interacting with ghosts. Let's all back. I know that. Stop sharing, Dr. Omorege. Stop sharing.
Somebody seems to be in Bahamas.
Is it I'm in Bahamas? Okay, that thing I said.
Yes.
Okay. Okay. Yes, it's just a background, the partial background. Okay, maybe the light. Yes. Can you see my face? Maybe the lights. Maybe the direction.
Yes, we can.
Yeah. So,
sir, I would like to ask one question, sir, please.
Oh, ask your question.
Okay, sir. If somebody comes now and said he wants you to help him to analyze his data, what should somebody be looking out for?
If somebody wants you to help him or enter data, right? Analyze data.
Yes.
Yes. What should you be looking for, right? Yes. Yes. You have to understand the study design. Yes. You understand? You must understand. Okay. What is the title of your study? You want to know the objectives. You want to know when you know the objective, then let the person give you the instrument You see the tools. And you can off your this now. You see the tool, you can off your camera. You see the tools. When I mean to do the questionnaire, because let me a lot of people, the variable, even the objective is not speaking and they are titled, they are not speaking together. Even some people, the variable they have collected in the questionnaire, there are some objectives that are not answered. I don't know if you understand me now. So you need to understand, and the type of analysis you will do also depends on the study design. If it's one group study or comparative or whatever, you need to know. The outcome measure, you need to ask what is the variable, your outcome measure. That is like now, if it is socioeconomic status, the outcome, or is it diabetic glycemic control? So you need to understand. And the way they want to measure the glycemic control, is it something that you are measuring quantitatively, like somebody say hemoglobin concentration? The hemoglobin concentration, you know that you can calculate the mean and standard deviation. But you want to have a cutoff and say anemic, all those things will be factored in. You have to understand it. You have to ask them. And that is why they usually tell people, before you even go submit proposal, your proposal stage, you go be statistician. Because it's from that stage that we make the work analyzable. Otherwise, they have gone to the field, they have, in fact, there are many people that brought they brought data. The data, they are not, the data is not answering the research question. It has happened. But they don't know. So this thing now, the more you do, practicalize, get more knowledge. So what you can do is that you can even start with somebody, okay, you want to analyze, let me help you. You may not charge the person, let me help you. You know, people are graceful when people want to help them. They want, everybody wants free thing. Do your data, let me analyze it. Let me help you. So you practice with it now, and you now give it to him. So you have tried your best, if any other thing. So if he's not satisfied, you cannot answer all the questions, he can seek help. In the process you are learning, you will now reach a stage that you have your confidence, you do some. You ask, about your, I've submitted, there's no problem. You yourself begin to feel that, yes, I'm getting it. Or maybe even it's for publication. They will send it for review, and if they have questions, can you still help me do this one? They say we should do this one. You can do it. Anything you cannot do, this one you cannot do. So in the process, as time goes on, you discover that you are able to tackle a lot of problems. That's the way to do it. You have to read about it and practicalize it. Read about it, practicalize it. Read about it, get more knowledge of it. So you see, it's not enough. The knowledge of statistics is more important than using SPSS. Some people, they just say, okay, they just know how to run. Anybody can, also on these smart people from secondary school, they can just, if you ask them to help you use SPSS to analyze them, maybe to enter data, you teach them, help me input this data. By the time they finish, they now look at, analyze. They just click, analyze, and move one variable. The thing just wrong. The next thing, you put their number, they put say that if you want to analyze your data, call this number. A lot of people, they are some funny doctors, they are fall victim of that type of thing. Number one, it's going to be difficult for somebody that is not even a doctor to understand. Even someone that is a professor of statistics, maybe in the university, if it's not in your line, it may find difficult. You know, medical line is a specialized area. It's not, the data is not like maybe football data, everyday data that yes, anybody can. But this one now, when they are talking of glycemic control, so you need to understand some things. It is easier for a fellow doctor, or you that are a doctor, or someone in medical line to handle the data down. The people that are not there. I don't know if you have you were in one of my lecture on the logic of scientific reasoning, or you can in the YouTube you can watch it. The logic of scientific reason. I stated there that is biologists that develop statistics over the years. All these Fisher you hear, Pearson, all those they were geneticists. So the geneticists, most of the people that developed statistics they were either biologists or social sciences. Biologists first, most of them are biology, then some social sciences. So all these other people in the department of mathematics, in science, pure science like chemistry, physics, because they don't need the statistics like you. That's why they don't contribute. So people that contributed is that because your measurement in biology and social science vary a lot. It follows what you call probabilistic model. Whereas all those physical science like physics and chemistry, the phenomenon follow the deterministic model. So for example, now if you talk about Boyle's law, Charles' law, it's the same. You perform experiment, you want to know what constitutes water. If you go to Tupu and do it, it gives you the same. You go to Canada and do it the same. If you don't get the same result, maybe your method, you didn't follow the right method. But the discrimination against HIV, is it the same in Canada and Nigeria? Even in Nigeria, it's not the same thing in the north and the south. It's not in the same, even in the same state, it's not in the same thing in different local governments. So you see, social science issue, then biological issue, like as you are sitting now, if they take your blood now and check the blood sugar, and within 1 minute and take another sample, you will not get the same because there's variation going on. Even your blood pressure as you are sitting down, that is why in intensive care unit, they connect this thing to measure the vital sign. Within 1 minute, it's in the range. It's fluctuating because a lot of things are going on, traffic in the inside. So the biology, it vary, everything vary. No, your blood sugar now is different from your blood sugar a minute after. Your cholesterol now is different from your cholesterol before. After you have eaten, may increase or decrease. No, there's variation going on when it comes to biology and social science. So unlike the physical science. So that is why the biologists develop over the years, the people that are good at statistics, you are biologists. Let me just close by just giving you this gist. When I was in Lutz doing my residency in public health, and I also did my MPH because they do allow us to do MPH as I do residency. So that was when the Lutz they started the College of Medicine there. They started all those epidemiology master and epidemiology management by statistics. So there was the one guy who's a physiotherapist. He was doing statistics. Most of them, I analyzed their data. Even though I was doing MPH, he was doing biostatistics. I handled his data. He was not telling me what they were when he brought some issue, I was helping him to solve it. He now said that when they were in class one day, one of the professors of statistics they brought from Unilag to take them, he was asking them, say, how many of you are physicians here? So those people that were doctors now raised their hand. He now say, he will encourage them to go into statistics. The man is not a doctor, a medical doctor, but he's a professor of statistics in Unilag. He now said that, why he said that was that his best teacher in statistics ever was a medical doctor. That the man was late then. He said his best teacher ever in statistics was a doctor. This was a professor of statistics talking. He said that he said doctors by nature of their work, they persevere. He said that the statistics require perseverance. For you to know statistics, you require doctors by the nature of their work, they persevere. And that is why if they go into statistics, they excel. So that one is just, he's able to get that from experience. But if you study very well literature, the people that develop statistics, there are biologists that develop statistics over the years, they were biologists. So Fisher that invented all these, Fisher exact, all those ANOVA, Fisher, all those things, Pearson that describe correlation, and first of all, calling standard deviation, that invented this Pearson chi-square. They were geneticists, they were biologists. So you see, so if you all you need to do is to exercise patient very well. You study and you are practicalizing it. The sky is your limit. So I think we can stop here.
Thank
I'm
you,
supposed to even pause. I'm just recording all.
When I see data.
When you watch?
When I see data that I want to analyze, I become confused about the choice of a test statistics that I'm supposed to use for that particular data.
Yes, okay.
So I was looking for all these tables. There are some tables that people develop where they tell you, okay, if the the outcome is dichotomous,
Okay, I don't worry. I've presented. You know, if you have been following my lecture, you go and even Google freely, even without registering. Google $2 for YouTube. There are some lecture where I talk about last year lecture. They are there. Choosing statistical tests is there. Go and listen. Choosing statistical tests.
Okay. Okay.
Choosing statistical tests.
I don't have your website address.
Even that one is on YouTube free. If you just Google YouTube, my website there, I will send it to you. It's on the platform now. I put it leveragestart.com. Leveragestart.com. But you cannot access anything through my website unless you register. But you can access the lectures to just Google $2 YouTube to take you there. But if you want to get all the workshop we have done, demonstrate, you can if you register. Like one lady, she is ONG report.